Hello everyone, a very good morning to all. Today I am going to present some interesting concept of digital counters such as their types, their construction and how they work on behalf of switching theory and logical design, focusing more on decade synchronous counters. I am Shrestha Sagar from BTech CSE of USICT GGSIP University. Before heading on towards our main topic, that is decade synchronous counters, it is necessary for all to be familiar with these terms I will be discussing throughout the PPT very frequently. Combinational circuits. It is a circuit in which present output depends only on present input. Sequential circuits. It is a type of circuit in which present input depends on sequence of past inputs as well along with present input. Flip-flops. Flip-flop is a circuit that has two stable states and can be used to store data information or state information and frequency distribution also. T flip-flops. It stands for data flip-flops and hence when we have to store only data we use T flip-flops. T flip-flops. It is a type of toggling flip-flops. It can be constructed by combining the input of J and K in JK flip-flop. Now the question arises, what our digital counter is? It is a sequential circuit that simply counts. A digital binary counter is a device used for counting binary numbers. Digital counters mainly use flip-flops and some combinational circuits for special features. Hence, when we have to apply some special features, we use some combinational circuits of some flip-flops in digital counters. As we know, flip-flop operates on clock pulses, so the counter will count up or down using these pulses. The two types of digital counters are asynchronous counters and synchronous counters. Both of these have their own 4 different types, but we will be focusing more on here a specific type of synchronous counters, that is decade synchronous counter. But before moving on to decade synchronous counter, we must know what a synchronous counter is. In synchronous counter, the external clock pulse is applied to all the flip-flops simultaneously. Hope you get the meaning behind this. Let me explain. In synchronous counters, the clock input of all the flip-flops are connected together and are triggered by input pulses. Thus, all the flip-flops change state simultaneously. Hence, the states of flip-flops change simultaneously in synchronous counters. But what is the advantage behind this? The advantage of synchronous counter is that there is no cumulative time delay because all flip-flops are triggered in parallel. Decade synchronous counters. As the name suggests, it might be a counter that can count to 10 decimal states. Yes, you guessed it right. Basically, a decade synchronous counter is a modified binary counter with mode value n is equals to 10. A basic decade counter is an electronic circuit with a 4-bit binary output and an input signal called as clock. With each clock pulse, the output advances to the next higher value, resetting to 0000 when the output is 1001 and a subsequent clock pulse is received. The more familiar way to explain this is whenever the counter reaches to 1001, that is decimal equivalent 9, it resets its value back to 0 and the process goes on and we have a counter that can count 10 states. Where are decade counters used? Decade counters are used in clock circuits, frequency dividers, state machines and sequencers, etc. Decade counter is a modified binary counter with mode value n is equals to 10. Mode is the number of states that can counter have. Hence, a decade counter can have 10 states and n value is equals to 10 here. It has 10 states representing one of 10 decimal numbers, which is why it is known as BCD counter. The default state of decade or BCD counter is 0000. When it reaches decimal counter 10, it resets to 0. Here, the circuit diagram of decade 4-bit synchronous counters. As you can look in the figure, the decade 4-bit synchronous counter consists of 4 JK flip-flops, 4 AND gates and 1 OR gate. The first flip-flop, that is FFA, is at least significant bit and the fourth flip-flop FFD represents most significant bit. It is an important one. The input value J of FFA flip-flop is connected to logic 1. That is, the first flip-flop is a toggle flip-flop. It is an important point to notice. In the beginning, all the states, that is the outputs or Q values, are reset to 0 and the counter is also resetted to 0. When the clock pulse receives first negative edge, the Q1 toggles to 1 because due to toggling nature of first flip-flop, and the counter raises its value by 1 and the counter outputs 1. At the arrival of second negative edge clock pulse, Q1 toggles back to logic 0 state and hence the input given to the second flip-flop turns to logic 1 due to 0 input in AND gate. And that is how the counter basically moves from state count 1 to 2. Similarly, the process goes on and the counter reaches 1001 state, that is 9th state. When output of counter reaches 9th state, output of Q1 and Q4 remain in logic 1 state. And hence, for the next step, the counter resets its value to 0. It will be more clear from the state table. Here, in the beginning present state, all the values Q1, Q2, Q3 and Q4 are set to 0. Then the toggling nature of F1 flip-flop makes Q1 1 and hence the counter sets to 1. When the second negative edge cycle reached the logic 0 state and hence the output given to the second flip-flop turns to logic 1. That is why counter changes its state from 1 to 2. We can clearly see from the table the next states and flip-flop inputs. Now, working of decade counters. How are the states changing? More clearly, we will discuss here. The additional AND gate detects when the counting sequence reaches 1001, that is binary 10, and causes flip-flop FF3 or FFC to toggle on next clock pulse. Flip-flop FFC toggles on every clock pulse, thus the count is reset and start over again and 0000, producing a synchronous decade counter. We could quite easily rearrange the additional AND gates in the above counters to produce other count numbers such as mode 12 counter, which counts 12 states from 0000 to 1011, that is 0 to 11 in decimal, and then resets to 0. Construction of decade synchronous counters. A decade counter or BCD counter which can count 0 to can be made by cascading flip-flops. That is, simultaneously or arranging some circuits of flip-flops can be used for constructing decade counters. But a standard binary counter can be converted to a decade counter with the aid of some additional logic implement the desired state sequence. After reaching the count of 1001, the counter recycles back to 0000. Decade or BCD synchronous counter can also be designed using T flip-flops and D flip-flops. The designing of decade counter using T flip-flop is same as up counter, but there is a condition: when the count or state reaches to 1000, it will clear all the flip-flops to default state. Flip-flops normally have active low clear, so we have to apply combinational circuit to automatically reset the circuit upon reaching 1010 state. The combinational circuit should produce 0 to clear flip-flops. Have a look at the circuit diagram of T flip-flops. Here, the first flip-flop is a triggered flip-flop and set to logic 1. There are 4 T flip-flops, 2 AND gates. and a NAND gate. Design using D flip-flop. Decade counter using D flip-flop is a modified D flip-flop's up counter. Hence, it is a modified version of D flip-flop up counter. The modification it needs is the auto reset function. Upon reaching the state 1010, which is decimal 10, reset function will clear the flip-flop to default state 0000 to start the count again from 0. The combinational circuit for reset function is same as in T-flop flip-flop BCD counter. BCD counters are used in digital clock and event counting. This is the simple circuit diagram of decade synchronous counter constructed using D flip-flop. There are 4 D flip-flops and 2 AND gates, 1 NAND gates and 3 XOR gates.